for lately. I need this open. Wonderful. So we are in chapter 10 now. I sent some emails over the last few days, so you probably would have seen, well, hopefully you did the assignment that was due last night. The second assignment has now been posted, and that'll be due next Tuesday, so that will cover most of the stuff from chapter 10. I sent in some information too about the quiz that starts next week, and my plan was to open that Friday, where we would have had, by that point, 3 sort of full classes of chapter 10 material. I expect by the end of that class, everything that's on that quiz will have been covered. But if not, there might be some stuff on Monday, but I'm not really expecting that to be the case. The quiz at the moment has 17 questions, and I might try to make it around 20. But I don't expect time will be an issue for this. Like, it's pretty quick. I don't think this isn't going to be like a race against the clock. That said, because this is a timed Acorn quiz, what that means is the second you start the quiz, the timer starts. So if you log in, do 1-2 questions, and then go to bed, it's not going to be active for you in the morning. So make sure that when you start, you actually do the entire thing and finish it. The quiz is going to be open book, so you can use any resources you want. Anything that's on Acorn, it's fair game. But as I said, it has to be done individually. No working together, no sending each other answers, and no posting questions to online forums or hiring somebody else to do your test for you, as I'm dealing with right now in this course. Actually, not in any of my courses. So that's one of the nice things about being department head, is you get to deal with all of the things that happen in the entire unit. Very fun. So where does that take us? I think we're ticking right along. We've got everything done so far that we promised we'd be getting done. Hopefully labs are going well this semester. All right, let's keep going. Specific heat capacities. So this is kind of where we finished up at the end of last class, talking about specific heat capacities. And this is really the amount of heat or thermal energy that a substance can absorb in order to raise its temperature by 1 degree Celsius or 1 degree Kelvin. Of course, that's the same measure. If you 1 degree increase or decrease is the same in Kelvin and degrees Celsius. So you see the symbol that we use for specific heat capacity is C subscript S, small c subscript s, and the units that we often find here are joules per k gram, or sometimes you also see joules per degree Celsius gram. So one or the other, really the same number. And we kind of looked at this at last class. We compared a couple of things. We saw that copper has 3 times the specific heat capacity as gold. So pure substance, so a pure, say, kilogram of copper would take 3 times the amount of energy or 3 times the amount of heat to bring its temperature up 1 degree than the equivalent mass of gold. And when I say mass, it's because it's always expressed per gram of material. So this specific heat capacity, this small c subscript s, is only used when we're looking at pure substances or pure homogeneous solutions as well. If you had a more complex system like a frog or a house or something that is not homogeneous, we would not use specific heat capacity. We would use capital C, which is the heat capacity for the entire object, which we talked about last class as well. Great. So I have a couple of examples, and maybe we could start today's class off by looking at a few of these examples and how to deal with them. First one says, how much heat in kilojoules is needed to bring 1.5 liters of water at room temperature to its boiling point? And this is going to be equal to Q equals MCS delta T. And the mass of the water, we need to have in units that match our units for CS, which you can see here is in grams. So we need to put our liters of water in grams. If it is indeed pure water, that'll be 1,500 grams. Times our CS. Times our delta T. So if its boiling point is 100 degrees Celsius and its current temperature is 21, then our delta T is going to be plus 79. And I put K here, even though we have degrees Celsius in the example, and that's just because degrees Celsius and K are the same units when we're dealing with delta T. Not absolute temperature, but change in temperature, delta T, those are the same number. Great. So what does that give us? I have this calculated out already. So this equals, not that one, there we go. This equals 4,95330. See, grams go, K go, and that gives us units of joules. And the question is asking us for this value in kilojoules, so we would divide by 1,000. 495 kilojoules, and even that is probably too many sig figs. Think about it. Probably what we might want here is 5.0 times 10 to the 2 kilojoules. Although I'm typically not that fussy about sig figs if you're plus or minus 1. But yeah, this would be the official correct answer to the correct number of sig figs, which is limited by our volume of water. I'm not sure how you guys deal with significant figures. The way I usually do it is I carry extra significant figures throughout the and then at the end round it back to what the minimum number was starting out. Saves you a lot of sort of calculations along the line. Here's another example. This one is saying a 100 ml sample of water is heated from 298 to 328. How much heat did this require? This is really the exact same question. Q equals MCS delta T, and the mass here will be 100 grams because the density of water is 1. 4.18 joules, K to the minus 1 grams to the minus 1. And going from 298 to 328 is 30 K. And that gives us, in the end, 12540 joules. And we would want to bring this down to kilojoules, 12.5 kilojoules to the correct number of sig figs. These kind of calculations aren't too taxing, I don't think. There's another kind of question, though, that we give, which is maybe a little more complex. And I'm going to show you that type of example when we go to the next question. This question looks like this. A hot marble stone weighing 3.40 kilograms is dropped into a tub containing 100 liters of water at 21 degrees Celsius. Once the system comes to thermal equilibrium, the temperature of the water and the marble is 27.2 degrees Celsius. What was the original temperature of the marble stone? So this is the way they used to heat up bathtubs. And what does that remind me of? Did you ever see Crouching Tiger, Hidden Dragon? No? It's a good movie. It's got subtitles, but I don't know why. Having seen that movie doesn't increase your understanding at all of this. But you get what we're doing here is we're heating up a rock in a fire or whatever, dropping it in a tub and using the heat transfer from the rock to the water in order to heat up the water in the tub. So the way we would look at this is we would say that the Q of the water is going to be equal to the negative Q of the stone. In other words, the heat that's absorbed by the water is going to be the same value as the heat lost by the stone. Okay, and we have Q as being, I guess, positive for the water because the water is gaining energy and the stone is losing it, so we're going to put a minus in front of it. So the quantity is going to be the same, the only difference is going to be the sign. So we know what the Q water is going to be. QW we'll say instead of Q water, just to save me letters here. That's going to be the MCS delta T for the water. And the mass of the water, we're starting with 100 liters, which actually isn't that much, is it? Does that fill a bathtub? I don't think so. 100 liters. 1,000 liters would be a meter cubed. So 100 liters would be like 10 centimeters deep and 1 meter by 1 meter. So half a meter. That could be a decent bathtub, I guess. Anyway, 100 liters, we're going to go 100,000 grams, 4.18 joules, k to the minus 1 grams to the minus 1. And our delta T is going from 21 degrees Celsius up to 27.2 degrees Celsius, which is an increase of 6.2 degrees Celsius or K. And that equals 2,590,000 joules. So that's how much energy was gained by the water. And that same amount was lost by the marble. So of course it's going to be negative because it's being lost. So the negative is just telling you whether it's lost or gained. So we would say then that the Q marble equals negative 2,590,000 equals, we're told that the rock weighs 3.40 kilograms, which is 3,400 grams. We're given the specific heat capacity for the marble, 0.880 joules, k to the minus 1 grams to the minus 1. And then our delta T. So all we really need to do here is solve for delta T, divide each side by 3,400 times 0.880, and we're going to get a value for T that's a negative number, which is good. So our delta T, if you solve this, delta T equals negative 866. So what was our initial T? Well, our initial T, TF minus T initial. Our T final is 27.2 degrees Celsius. I'm kind of running out of space here, but we come up here, say, then we can calculate our initial temperature, which is going to be equal to 893 degrees C. So it's pretty hot, probably not red hot. That would be about the temperature of like a regular fire flame. So if you had that sitting in the coals of a wood fire, I wouldn't be surprised to see that it went up to 893 degrees Celsius. And then that would make sense. Drop it in the water, do that a couple of times, and you might get it up, fairly warm. So this one really, it's the same type of question as the previous examples. It's just maybe a little bit extra because you have to just realize that the heat gained from one is the heat lost from the next one. Okay, so what we want to do is differentiate between two types of functions, and this is broadly applicable outside of this particular course, or this particular topic, where we like to differentiate between functions that depend on the route that is taken, like a path function, versus a state function, which is one that only depends on the initial and final states. It doesn't matter how you get from the initial state to the final state. All that matters is where you started and where you finished. And so for an example here, let's say you are driving from Wolfville to Truro. And what I've drawn here is two different routes. You can take the main highway, turn around just before Halifax, which would be, this path, follow the highway the whole way. Or there's another path, there's an exit near Windsor where you can kind of go on the back road through Highway 236. According to Google Maps, the Highway 236 route is 50 kilometers shorter. But which is faster is a different question, because I think the maximum speed limit on the back road is 80, and the maximum speed limit on the other road is 110. And if you get stuck behind somebody slow, or a school bus or something like that, or a tractor on the back road, it can end up taking more time. I've done both many times, and it turns out to be roughly equivalent. But definitely this one is 50 kilometers shorter. And what we're doing here in the end is we're traveling from Wolfville to Truro. So our net displacement, doesn't matter which route you take, or your change in altitude from your initial to your final spot, doesn't matter which route you take. Both of those would be examples of state functions. The amount of gas you burn, though, would be very dependent on which of these two paths you took. The time required to drive would also depend on which of these two paths you took. That would be an example of path function. Right? So some things in chemistry depend on the path, some things don't, as you'll see. Yeah, state function does not depend on the route, saying the exact same thing. So what we want to do is define something called enthalpy change, and you've probably been using enthalpy all throughout this course, and we're going to look at it in just a little more detail now. Enthalpy change is just the heat transferred during a chemical process carried out at constant pressure. So it's basically, sometimes we just call it QP, which means it's Q, heat transferred in and out of a system when the reaction is taking place at constant pressure. So many of the reactions we do happen at constant pressure. An example might be, anything that's just in an open flask, because it's under atmospheric pressure and it can expand or contract as necessary. Pressure is always constant in a reaction like that. Biologically, I think almost all biological reactions take place under constant pressure conditions. There's definitely different pressures in different parts of our bodies, like, in your arteries, the pressure is much higher than in just your general cells or in your brain or whatever. But for most chemical reactions, I would say that pressure is held constant. If you have like a controlled explosion or, a reaction inside a pressurized vessel or these sorts of things, you can have examples where the enthalpy change Q is not a constant pressure, but most of the time it will be. So all this is Q for a given reaction, and it's often expressed in units of energy per mole. So it's sort of it gives you the amount of energy that you would expect to get for a given chemical process for every mole that's used. So this is an example, combustion of methane. Methane reacts with oxygen to make carbon dioxide and water. This has a delta H of negative 890 kilojoules per mole. And it's negative because it's exothermic, and that's because the system, which is this reaction, is giving off the heat. And so the system you can think of as losing energy, which is going to the surroundings in the form of heat. Just a note on how this is drawn right here. I know when I was in high school, we wrote these differently. We wrote them like this, delta HR, or maybe like delta H reaction. And up until a few years ago, most students that were coming in came to expect that. Sometime in the last 5 to 10 years, IUPAC changed the way they wanted this written to look like this. So we changed too. So we're doing this in the correct way. But depending on whether your high school caught up to this convention or not, you may have seen it in any one of these two forms. Do you know which form you might have seen this in before, if you've ever seen delta H? You've seen like the bottom one? Yeah. Yeah. There's a few other things, like IUPAC keeps changing, like small things, and we try to keep up to date as best we can. For all thermochemical equations, the standard unit of pressure is now the bar, which I know when I went to high school, it was atmospheres. So everything was in atmospheres. They got rid of atmospheres and switched to bar. Bar is arguably a better unit because it's based on other SI units like the Pascal, the Newton, the meter squared, all these sorts of things. Where atmosphere was, I think, chosen for a long time because it was like convenient because of the atmospheric pressure, even though that can vary as well. Bars and atmospheres are very close to each other, but bar is the standard unit that we should be using for all of our measurements going forward. And that was a change within the last 5-6 years as well. So yeah, we do try to keep up to date. When you buy new textbooks, like every couple of years, they put a new textbook out and charge an additional $200 or something like that. Those are the types of changes that are being made. They keep trying to update the textbooks to have the latest, even though the actual fundamental chemistry going on is not changing. The way it's presented sometimes changes a little bit for reasons. People get really passionate about those reasons. Enthalpy, delta H, is enthalpy change, I should say, delta H. For some process is a state function, meaning all that matters for finding delta H for a process is where you started and where you began. It doesn't matter which path you took. You could imagine number of possible paths going from A to B. This is just showing it's a reaction. Sodium metal reacting with half a mole of chlorine gas is going to NaCl solid. This is just one possible path that you could do to convert the reactants to products. It doesn't matter what the actual path is if you can find a possible path and figure out for every step what the delta H is for each of the steps. You can just add all the steps together and calculate the overall delta H for the reaction, even though if that isn't the path you took, because it doesn't matter. All that matters is the initial state and the final state. This is true for delta H. Going forward, it's going to be true for delta S and delta G as well, which will be coming up in the next unit. All right, so we have delta H's for a bunch of different situations. We have the standard enthalpy of fusion, and that is the delta H associated with melting a solid. And this is done at 1 bar pressure. And when it's done at 1 bar pressure, we say this is under standard conditions, because remember, delta H is just Q at a constant pressure. So if you're at a constant pressure, whatever that constant pressure may be, you'll get a delta H at that value. So if you're at 1 bar, delta H is at standard conditions, and we give it this little symbol. Looks like a theta. That theta just means we're at 1 bar pressure. We're under standard conditions. And this value, this delta H of fusion, you can find tables for all sorts of things. It also assumes that melting is happening at the melting point of that particular substance. So for water, for example, water's melting point is 0 degrees Celsius. If you take ice and it starts to melt at a higher temperature than that, for whatever reason, that delta H will be a slightly different value. So it's defined as 1 bar pressure and the melting point of that particular substance. And so you can see in this table here just a number of random chemicals. Water's there because water is probably most important. It shows its melting point there and the standard enthalpy of fusion for that process. This is another change, I'd say, that's happened. This one's probably a little older change, but we, instead of calling it enthalpy of fusion, we used to call it heat of fusion. Or like heat of reaction or heat of whatever it is. If you ever see that written down somewhere, that means the same thing as enthalpy. Heat of reaction is enthalpy of reaction. All right, so we have these standard values. There are tables of these. There's a book called the CRC Handbook of Chemistry and Physics, which has thousands of compounds with these numbers in there. Now you find this information online. Often, if you Google a chemical on its Wikipedia page, this information is there. There's also the NIST Handbook, which is another online resource. It's free, where you can get all this kind of information as well for all sorts of different substances. The things that people bothered to measure, at least. Example, 100 mil sample of ice is heated from 260K to 328K. How much heat did this require? So this one's kind of interesting because we're starting at ice and we're changing phases in here. So really, what's going on? You can think of it like this. We have heat added. This would be the temperature, right? And we're starting at 260. So when you add heat to this ice, what it's going to do first is raise its temperature. It's not going to change phase until it reaches its melting point. So adding the heat is going to cause the temperature to go up until we hit its melting point, Tm. And what's the melting point of water? See it in our table right here. That would be 273.2. Then when you add heat, it's not going to warm it up at all. All the heat is going to do is go into changing the phase. So just by changing phase, that ice going from liquid from solid to liquid is going to be absorbing that heat. So adding additional heat, that's supposed to be a horizontal line here. So all that's happening with that added heat is a phase change. Then, once we melt that completely, all the solid has converted to liquid. Then adding more heat will then start to warm up that water. It would look like this. And we're trying to go from 260, the final temperature, of 328K. So I look at this and I see sort of three phases. There's phase A, phase B, and phase C. And we would use a different equation to calculate the heat absorbed in each one of those three steps. Notice my slope for A and C are different. The slope for C is like double the slope for A. I did that on purpose. Although probably what I should have done was make A twice the slope of C. Just looking at these CS values, they're roughly double each other. That means you require twice as much heat to raise the liquid water by 1 degree. So really C should have a much lower slope than A here. But we're not going to worry too much about that at this point. Okay, so we have phase A, phase B, and phase C. We want to do the calculations for each of those. All right, so for phase A, Q equals MCS delta T. This is just raising the temperature of a substance. The mass of water is 100 grams. Yeah, I'm going to change this to grams just because 100 mil sample of ice, because the density of ice isn't exactly 1. Technically, 100 grams is not 100 mils of ice. So I'm going to change this to 100 grams to make my life easy. CS for solid water, because we're still in the ice phase, it's 2.11 joules per k gram. And the delta T is the temperature required, the temperature difference from 260 up to the melting point. Melting point is 273.2, so this number is 13.2. Okay. And that value is 2743 joules. So once you put that much heat in, all you've done is brought the ice up to the point where it's now able to melt. Once you arrive here, then now we can start doing the melting. B. So now we're in phase B, and all we're doing here is melting the ice. Q is going to be equal to delta H of fusion times the number of moles that's reacting. So that equals the delta H of fusion here. That's in kilojoules, by the way. 6010 joules per mole times the number of moles. We're given number of grams. That's mass over molar mass. Just 100 grams over what, 18.02 grams per mole for water. That equals 33389 joules. The biggest mistake here by far, I would say, is people forgetting to convert between joules and kilojoules and that kind of thing. C, Q equals, in phase C, we're just heating the water now. We're still at 100 grams. Yes, for the water is 4.18 joules per kgram. And delta T is going from 273.2 up to 328. And what does that equal? 27 plus 28 is 55. And I realize there's a 0.2 there I'm dropping, but I guess if you're subtracting it from 328, that's not a significant digit. And that gives you 22990 joules. So what you can see is that, you know, phase B is the most important of the three phases here in terms of the amount of heat that's being absorbed. So think about that when you are, next time you are making yourself a cold drink, and you put an ice cube in there. And the purpose of the ice cube, right, is to absorb heat and bring down the temperature of your drink. You sometimes see fancy ice cubes being sold online, like they're like little blocks of marble or something like that. And you put them in the freezer and they go down to 0 and you can drop them in your drink. Some people prefer those because it doesn't melt and dilute the drink, which some people get really, really care about that. But besides being a potential choking hazard, those things are not nearly as effective as ice, because most of the heat absorbed by putting an ice cube in your drink is the ice actually melting, changing phase. Not the fact that the ice is cold and it just absorbs energy to warm up. It's because it's melting and that's absorbing most of the energy. So if you put in something that doesn't melt, like a piece of stone, it's not going to have nearly the same impact. So the overall heat for this process is just QA plus QB plus QC, where this is QA, B, and C. Add those three up together and you get 59122 joules equals 59.1 kilojoules. That's the amount of heat that's required to go through this process. So I find it helpful often in these kinds of problems to draw a little diagram just to show you what it is that's happening in these situations and go from there. All right, we have other delta H's that we can learn about. We have delta H vaporization. which is delta vap H. Again, this is defined at 1 bar pressure, which is standard pressure, and it's the boiling point of the substance as well. So same deal as we had for melting temperature. So this is just the energy required to evaporate 1 mole. And evaporating 1 mole of a substance like water, for example, 40.7 kilojoules per mole is way higher than the energy required to melt the same amount of the same substance. So to melt 1 mole of water was only 6 kilojoules. To evaporate it is 40 kilojoules. So you think an ice cube melting is efficient at absorbing heat out of something. The same amount of water evaporating, way more. So this is actually like a very useful thing for us. It's how we regulate our body temperature. When you sweat and you have water evaporate off your body, I realize that's not at the boiling point of water. So that number that I circled here, that 40.7, will be a little bit different when you have sweat evaporating off your body, but the number will be similar. It'll be of the same magnitude. So this is a lot of energy that is required to boil something. The reason for that actually comes down right down to the intermolecular forces. Is when you melt something, you are keeping intact most of the intermolecular forces. There's still a lot of intermolecular forces holding a liquid together. When you boil something, you break all of the intermolecular forces. All of these need to be broken, and that requires significantly more energy. We also have the delta H of sublimation, and sublimation is the process of going directly from a solid to a gas. Carbon dioxide is what's pictured here. This is dry ice. So dry ice will directly change phase going from a solid to a gas. Water can do the same thing too. If you put water in your freezer, let's say a tray of ice cubes, and you leave it sit there for like a month, the ice cubes will start to shrivel and decrease in size. And that's not because they're melting, it's because they're slowly undergoing sublimation, losing water vapor. The opposite of sublimation is called deposition. Just like the opposite of evaporation is condensation, and the opposite of melting is freezing. So yeah, some substances can undergo sublimation, which is basically skipping the liquid phase directly. So going from, let's say, solid water up to gas phase water, you can think of this as having 2 possible paths. You can either melt it first, then boil or evaporate the resulting liquid, or you can do it all in one step, which is sublimation. And what we know is that it doesn't matter which of these paths that you follow. Delta H is a state function. It depends on its initial state and final state, not on the path taken to get there. Okay. So, yeah. So what this means is that the delta H of fusion plus the delta H of vaporization for every substance is going to be equal to its delta H of sublimation. And these are the standard values for all of these. And what you can see is that if you add together the delta H of fusion and vaporization, you get the delta H of sublimation, which is good. It's confirmation that this is indeed a state function. Okay, and one of the most important enthalpies that we're going to be dealing with is what we call enthalpy of reaction, which generally speaking is delta RH. And the enthalpy of reaction is often there's a lot of different variants where that little R is. So if it's like a combustion, sometimes you see that R changed for a C. If it's a dimerization reaction, you could put a DIM or something like that. It's all sorts of different types of reactions that are sometimes indicated by that letter that you see right there. Again, this means you're under standard conditions, standard pressure, which is 1 bar. Sometimes you see the temperature specified because delta H for a reaction can change slightly depending on the temperature. Often cases you don't see it. Often, in fact, the delta H fluctuation by changing the temperature is often ignored because it's very small. But the delta H is just if the reaction is carried out at 1 bar pressure, it's just the Q for that particular reaction expressed in a per mole fashion. You can see that right there, negative 92.2 kilojoules per mole. Negative indicates that when this reaction happens, it's exothermic because energy is leaving the system and going to the surroundings. Great. So yeah, you see reaction, combustion, formation, anything else you can imagine, any other kind of reaction, you sometimes see that put up there as well. You know what? I'm done. We're 5 minutes early, but the next chunk is kind of a piece that I want to tackle kind of in one go. I think we did good today anyway. Yeah, great. And thankfully, we do have a recording here. How are online people doing? Still awake? If not, you can always check the recording. Okay, I'm going to stop the recording now.